All right, go and take your homework handouts out if you would, please. Hold them up so that I can see that they are completed. And should look something like this. Good, good. I don't see a whole lot of work there, which makes me think you probably have a lot of wrong answers. Good.
Same thing for me.
I actually see a little bit more work on yours than I do with Ethan's. And then, were you able to get that handout off the out of the description? You did not. Okay. Just follow along best you can then. Yesterday, we were continuing on this theme of right triangles. And before, remember, we said if we have a right triangle and you're given two sides and you need the third side, class, you should use the Pythagorean theorem. But there's a couple of special triangles. Triangles where you don't need two sides to get the third side. You only need one side. And if you have that one side, you can get the other two. One of them is a triangle we call a 30, 60, 90 right triangle. Because the angles are 30 degrees, 60 degrees, and 90 degrees, and mathematicians are not creative. So it's got angles of 30, 60, and 90. What should we call this? I've got it. What? 30, 60, 90? I like it. However, that came down, 30, 60, 90 right triangle. We need to know how to label the sides. And Ethan, that's what I was looking for on the work was, did the sides get labeled? Well, one of the sides, at least, has to be x. Which side?
The bottom.
Not necessarily the bottom.
The one across from 30.
The one across from the 30, and that's the way we want to think of it, is the one across from 30 gets to be x. Because you realize I could draw the triangle this way. I could draw the triangle that way. And in fact, I will draw them in all kinds of crazy orientations. You've got to know whatever's across from the 30, that's the x. All right, what about to the other sides? Give me another side and how we would label it. Genesis?
2x.
Okay, and what is 2x?
The longest side.
The longest side, which is the hypotenuse. Remember, it's not double angle, double side, but rather, remember, this comes from the idea of having an equilateral triangle. If this side is x, if you kind of flip the triangle over itself, this side would also be x, hence you get a side of 2x. There's 60 degrees, there's 60 degrees, there's 60 degrees, 2x, 2x, 2x all the way around. And then the altitude, or this long leg, technically, across from the 60 would be represented how, Kendall? X times the square root of 3. And again, it doesn't matter how it's oriented. The hypotenuse is 2x, and the long leg across from the 60 is x times the square root of 3. You just have to memorize that relationship, and recommended that you label that on each triangle that we draw. The other special triangle is sometimes called an isosceles right triangle, but it's also called a 45, 45, 90. Equal sides, equal angles. Which side gets to be x here, Jamie?
The one across from the 45?
Well, there's two 45s. Which one?
The short one?
It doesn't matter.
Both.
Okay.
Both, right? Both across from both 45s gets to be x. Okay, so yes, across from 45, both of them are x. Coming back to Jamie for redemption, how would we represent the length of the hypotenuse?
X times the square root of 2?
Good, x times the square root of 2. And again, it doesn't matter how it's oriented. It can be oriented very unusually. But if it's a 45, 45, 90, x times the square root of 2. Really doesn't matter how we draw it, as long as you make sure the hypotenuse is the x squared root of 2 and the legs are the x. Questions on this? Let's see how we did on the handout then. And Kendall, let me go and give you a copy of the handout. You can kind of do it along with us. Certainly use this for study purposes. And Audrey, so that you get the full benefit of this, make sure you actually print the handout and complete it. Of course, Kendall was sick and puking her guts up yesterday, so I can't give Kendall a homework offense, but you know. All right. Glad that she's way back there and I'm way up here. Oh, sorry, Chris. All right, let's go and take a look at the first problem. We were given our right triangle, and this time I had the 60 degree and the 30 degree angles written in. But again, normally, one arc, two arcs to show the 30, 60, 90. And I labeled this side as 8 inches. And for answer 1 and answer 2, wanted to find those lengths. The first thing we want to do, Quentin, is to label. I should label this I should label this and this.
2x.
And again, when you label the side with a given length, go ahead and say equals whatever. In this case, equals 2x. Well, from this, it should be pretty obvious, Quentin, that if 8 equals 2x, x must be 4. Well, number 2 is x, right? So number 2 is 4 inches. And number 1, I got blocked in there. Side number 1 is x times the square root of 3. Well, yeah, x is 4, so side 1 should be 4 times the square root of 3 inches. Did we get these answers for number 1 and number 2? Do we have 4 square root of 3 inches and 4 inches? Good. Going on to number 2. Given a 45, 45, 90. Again, normally we won't have these angles written in there. Normally there would just be an arc marking or equal side markings, either one of those. And again, the hypotenuse was given to be 8 inches. Needed sides 3 and side 4. And again, we want to start by labeling everything. And Ethan, how should I label this stuff?
X for the legs.
So side 3 is x, side 4 is also x.
And then x squared over 2 for the hypotenuse.
Good. The hypotenuse here was 8, which was equal to 2x. This is 8 is equal to x times the square root of 2. So here we had to divide away the 2 to get 4. So here to get x, we have to divide away the square root of 2. But we can't leave 8 over square root of 2, right? That's not rationalized. So we said, anytime you got a radical in the denominator, we should just multiply by that radical. So multiply by the square root of 2. And again, that's assuming a square root, some other, but in general, we're doing, yes, multiply by the radical. That'll give us 8 times the square root of 2 over the square root of, which of course is 2. And we could probably do that step in our head, right? The square root of 2 times the square root of 2 is 2. All right, but we can even further reduce that down to get
4 times square root of 2 inches.
and there's the length of side 4, which is x. Side 3, however, is x. So side 3 is going to have a length of
4 times
yeah, same thing. Same length, 4 times square root of 2. How many have 4 times square root of 2 inches for both 3 and 4? All right, questions on that? All right, let's go to numbers 5 and 6, back to the 30, 60, 90, and I'm going to be lazy here. And gave you 8 inches here, and this was number 5, this was number 6. Chris, what do we need to do?
Label
Okay?
2x, 6 is 2x, and then 5 is x times the square root of 3. 6 is equal to 16.
Well, I feel like we're missing a side. You
Oh,
labeled
8,
this.
sorry, I forgot to label it 8 inches. 8 inches is x.
Oh, okay, which means I don't need to solve for x this time. I know x this time, so
So number 6 is 16 inches.
because it's twice x, and if x is 8 twice, that would be 16.
And then 8 times the square root of 3, which I put as 2, which is wrong, I think, because I thought 8 cubed equals 2, so I didn't know that.
Ah, 8 times the square root of 3. That means 8 times 1.732 ... which would be somewhere in the neighborhood like 13.7, 13.8, something like that. So no. 8 times the square root of 3 inches. How many have this for number 5? This answer for number 6. Questions on that? All right, for the next ones, we were given another 45, 45, 90. I'm going to label it this way this time. Given 8 inches here, and then number 7 and number 8 in Genesis. What do I need to do first? Okay.
7 is, or where 7 is x. 8 is x times the square root of 2. And x equals 8.
Inches. The 8 inches is x. Okay, so for side 7,
8 inches.
also 8 inches, because it's x also. And then for number 8,
8 times the square root.
inches. And do we get these answers for 7 and 8? All right, good. And then for numbers 9 and 10, another 30, 60, 90 right triangle. And I give it 8 inches here, and asked for number 9 and number 10. And Jamie?
The 8 inches is equal to the x times square root of 3. 9 is x and 10 is 2x. And I'm trying to figure out, I put 8 times the square root of 3 all over, try and multiply square root of 3 both ways to where it would get out. I'm not sure why.
I think you're a step ahead of me. Did you divide away the square root of 3 first?
Not for that one, but for one of the others.
So solving for x,
Okay, yes, I guess.
which is down here.
Yes.
Right, solving for x, though, should have divided away the square root of 3 to get 8 divided by square root of 3. But you said you couldn't leave a radical in the bottom. That's why I assumed you had a radical in the bottom to begin with, okay? By dividing, trying to solve for x. But you said you couldn't leave the radical, so you did what?
I multiplied the square root of 3 on the top and bottom.
All right, and what did that give you for x?
8 times the square root of 3 all over square root of 9, which turns out to be 3.
And unfortunately, 8 and 3 don't reduce at all, but it's correct. It's ugly, but it's right. And there's our answer for number 9. 8 times the square root of 3 over 3 inches. How many had that for 9? Good. Then number 10, Jamie.
Would be 16 times the square root of 3 all over 3.
Good. 16 times the square root of 3 all over 3 inches. Remember, this is a 2 over 1, not 2 over 2, so we don't double the denominator. It's also not a radical 2, so we don't double the radical. It's only the coefficient of the radical that gets doubled. How many had 16 square root of 3 over 3 inches for the hypotenuse?
I got the other one, but I was thinking that 8 was x, so I just had 16.
Ah, okay. Questions on this? All right. Well, let's go ahead and set that aside. Let's do a little bit more practice. Maybe use the back side of the handout for some more practice. Kendall, did you feel that this was helpful review for you? Did this kind of help cement some things you saw in the video yesterday in your delirious state between... Anyways. I don't even know if she was really throwing up. I'm just giving her a hard time. All right, so let's go ahead and practice with some more triangles here. Given one side, find the other two. We'll get a little bit more creative shortly, but for now, each given side is 2 feet. Allows us to focus on the process and not worry so much about the number per se as we work. This is 7th graders, they're just whiny.
I remember this one, please.
Actually, I think it's 4th graders down the line. It's more fun to pick on 7th graders than 4th graders. I wanted to pick on 4th graders, you were a 4th grade teacher, a high school teacher, so I can pick on 7th graders. See how it works. Quinn's like, I you became a teacher because you wanted to impart wisdom and knowledge. No, Quentin. No.
Which you did. In order to teach us? No.
Just so I can pick on people. Chris has them. Quentin's got them. All right, for sake of time, pencils down, see how you did on the ones you got. We label the sides x squared of 3 for the long across from the 60, x for the short across from the 30, 2x for the hypotenuse. Well, if 2 feet is x, 4 feet is 2x, and 2 times the square root of 3 feet is 2 times the square root of 3. Here we could label the legs as x, the hypotenuse is x times the square root of 2, so of course if this x is 2 feet, this x is 2 feet, and of course this would be 2 times the square root of 2 feet. If this side is 2 feet, this is across from the 60, which this is the x squared of 3, this is the 30, across from that would be x, and then across here would be the hypotenuse, of course that would be 2x. Well, that means that x squared of 3 is 2. So just plain old x, you'd have to divide away the square root of 3 to get plain old x. Well, you can't leave 2 over square root of 3, so we'd multiply the top by square root of 3 and the bottom by square root of 3. Of course, that'd be the square root of 9, or just 3. And then the hypotenuse is twice that, which of course would be 4 times the square root of 3 over 3 feet. Over here we have another 45, 45, 90, indicated by equal angles. So of course the legs are x, the hypotenuse is x squared of 2, and that is 2 feet. So plain old x, you'd have to divide away the square root of 2 to get x. But we can't leave 2 over square root of 2. We'd have to multiply the top by the square root of 2 and the bottom by the square root of 2, which of course is just 2. And the 2's cancel, and we come up with just the square root of 2 feet. That's this x. Well, the other x, of course, would be the same thing, the square root of 2 feet. And here we have the long leg, which is the x times the square root of 3 as 2 feet. Of course, the short leg is x, the hypotenuse is 2x. You might be thinking, that looks an awful lot like this one. It is, it's the exact same. So x is still going to be 2 times the square root of 3 over 3 feet. And the hypotenuse still 4 times the square root of 3 over 3 feet. How do we do on these answers? Anyone perfect on all the ones you got done? All right, questions on any of these? Questions on any of these? Let's mix it up then.
Nice.
We'll leave the same triangles up. We'll change the information. Each of the given sides this time is 3 centimeters. Go.
No.
Okay, if you need to, that's fine. Chris is done, Genesis is done, Quentin is done. go and pause where you're at. Let's see how we did. 2x, x would be half. Divide by 2, 3/2 centimeters. Multiply x by the square root of 3 to get 3 times the square root of 3 over 2 centimeters. There's your first two answers. Here, this is x, this is also x. This is x times the square root of 2. This is x times the square root of 3. So to go to x, I have to divide away the square root of 3, which would be 3 over the square root of 3. Well, multiply top and bottom by square root of 3, get 3 times the square root of 3 over the square root of 9, which is 3, but that cancels and we're left with the square root of 3 centimeters for x, so 2x would be 2 times the square root of 3 centimeters. This is the x times the square root of 2. Divide away the square root of 2 to get 3 over the square root of 2, but top and bottom by square root of 2, get the square root of 4, which is 2, so we get 3 times the square root of 2, or 3 times the square root of 2 over 2 centimeters for x. This is also x. It's also 3 times the square root of 2 over 2 centimeters. And then this is x. So x times the square root of 3 would be 3 times the square root of 3 centimeters. 2x would be 6 centimeters. And in time, you will get to be just this fast too. How many got? All of the ones you did correct, even if you didn't finish them. All the ones you did, you got right. All right, questions on the ones that we missed, or do we understand them? Jamie?
So for the first one, we should keep it as an improper fact.
Yes, do not change to mixed numbers or I hate mixed numbers and decimals. Well, 1.5 wouldn't be so bad, but can you imagine 1.5 times the square root of 3?
Well, that's what I did. I had 1.5.
Yeah, 1.5 maybe isn't too bad, but 1.5 times the square root of 3 is just awful. I'll just leave it that way. All right, good question. Good. Any other questions?
So if I had 1.5 times square root of 3 over 3.
It's not entirely wrong. It just looks horrible.
Oh, so it's not wrong.
No, it's not. It's
Would
just
you take off points?
for instance, it would be nearly impossible to enter properly on your calculator.
Correct. Yeah.
So that's the reason why I hate it. So you know, when 3/2, 1.5, you know, there's nothing really to enter there. But once you get to a mixed number and a radical at the same time, it's rough. All right, one more round. We're gonna mix it up a little bit more this time. Fight. You can begin working once each one is drawn. So you can go ahead and start. Chris is finished. Quentin's finished. once you finish, check your answers. Still checking? Good. The third one. All right. Did you have this as the x squared of 3, this is the 2x, and this is the x? Were they at least labeled correctly? Or did you have them labeled wrong? Okay, if they're labeled wrong, obviously there's no hope, right? So it's got to start by labeling correctly, and then from there it's the algebra.
I got one.
Got them all right? And Genesis gave me a thumbs up, Kendall's good to go, and then Jamie.
I got to the third one.
Ooh, okay, gotta work a little quicker. Because again, part of the point of this is it's quick. It's an easy way to solve for things very quickly, which is something we want to be able to do there. Questions on the ones you were able to get done. And if you want to, Jamie, you can go back and watch the last part of the video or sections of the video to give yourself a little bit more practice if you feel you need it. For now, go and take out your notebooks. Turn to the Terms Definitions section. Terms Definitions section of your notebook. And we're, of course, going to continue reviewing over the special triangles a little bit in future lessons. We will be using special triangles the rest of the school year. So you won't be able to do things we're going to do later if you don't have these down, which is why I wanted to spend a protracted period of time working on these. But we're going to shift gears here just a little bit. And in your Terms Definitions section, I want you to go and write this term down. Perimeter, or the abbreviation is Theorem, P-R-I-M, of a polygon. Perimeter of a polygon. Very simply, the perimeter of a polygon is defined as the sum of the sides of a polygon. The sum of the sides of a polygon. Pretty straightforward. Now, there's all kinds of other little perimeter formulas you learned. We've done them in review exercises recently, or practice exercises recently, where you've, 4 times s for a square. Well, really, it's just s plus s plus s plus s condensed down, right? 2 lengths and 2 widths. Well, of course, because there's length, width, length, width. It's quicker to say 2l plus 2w, but really, you're just adding together the sides of a polygon. Any questions on perimeter? Theorem 65, down in the Theorem's Corollaries section of your notebook. We're going to talk through the proof, won't do the proof for sake of time. Theorem 65 in your notebooks, Theorem's Corollaries section, says this: the perimeters of 2 similar polygons, are to each other, the perimeters of 2 similar polygons are to each other as the ratio of any 2 corresponding sides. The perimeters of 2 similar polygons are to each other as any 2 corresponding sides. The perimeters of 2 similar polygons are to each other as any 2 corresponding sides. What did I say previously?
Ratio.
As the ratio of any 2 corresponding sides.
That's what I
It means
had.
the same thing. As the ratio of any 2 corresponding sides, but are to each other as implies a proportion, so yeah. Are to each other as any 2 corresponding sides, or as the ratio of any 2 corresponding sides would work. Means the same thing.
I was like, huh?
Sorry. I was writing and speaking at the same time, so just going off my notes there. Perimeters of 2 similar polygons are to each other as any 2 corresponding sides, or you could say as the ratio of any 2 corresponding sides. Here's the idea. You've got 2 polygons that are similar, and we'll go with some goofy looking shape there, and we'll go with some goofy looking shape here. Let's suppose we knew these were similar. That means that side A is to side A prime as side B is to side B prime, right? We call this ratio the ratio of similitude, right? As C is to C prime, as D is to D prime, as E is to E prime, correct? Well, remember we said the perimeter of a polygon is the sum of the sides. So the perimeter of polygon 1 would literally be what, Kendall? No. What would be the perimeter of polygon 1? Right. A plus B plus C plus D plus E. And if there were more sides, we just keep adding, right? The sum of the sides. The perimeter of polygon 2 would be what, Chris?
The how would you say that? A1?
A prime.
A prime plus B prime plus C prime plus D prime plus E prime.
There we go. That would be the perimeter. This theorem says that the perimeters are to each other. P1 is to P2 as any two corresponding sides. Let's just say C is to C prime. How would we arrive at that? Well, keep in mind, A is to A prime, we said, as B is to B prime, as C is to C prime, as D is to D prime, as E is to E prime, right? That's what makes these similars, the sides are proportional. Well, remember property 5 of your proportions was that in a series of equal ratios, the sum of the antecedents is to the sum of the consequence as any antecedent, maybe C, is to its consequent C prime. Well, if we know that A plus B plus C plus C plus E is to A prime plus B prime plus C prime plus D prime plus E prime as, I don't know, C is to C prime. Well, since A plus B plus C plus D plus E is perimeter 1, and A prime, well, those ones are perimeter 2, then yes, perimeter is to perimeter as side is to side. Last thing we'll write down, Brecken, you're dismissed, in your class notes section now. Last thing I want you to get down in your class notes section now. And we'll end on this note. And this is where we'll pick up tomorrow. Is that for similar polygons, the ratio of perimeters equals the ratio of similitude. For similar polygons, the ratio of perimeters equals the ratio of similitude. And then put a star next to this. Perimeter is to perimeter as side is to side. You're going to get that down in your class notes. Perimeter is to perimeter as side is to side. All right, we're going to pick up there tomorrow, but your homework is going to be more practice with these special triangles, making sure we're good to go with these. So homework is to do the handout that's in the description, and of course, Audrey, if you'll make sure you take care of doing that. Go ahead and complete the handout that's in the description of the video. We'll take a look at this tomorrow, and then we'll pick up talking about similar polygons and their perimeters. Have a wonderful rest of your day, and you are dismissed.